The binomial series can be written of the form f of x is 1 plus x to the k. Now let's look what happens when we find the Maclaurin expansion of this. Well, f of x is 1 plus x to the k. So f prime of x is k times 1 plus x to the k minus 1. F double prime of x is k times k minus 1 times 1 plus x to the k minus 2. The third derivative of x is, you see where we're going here, k minus 1, k minus 2 times 1 minus x to the k minus 3, so that the nth derivative of x is going to be k times k minus 1, and I'm just going to do dot 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 here, times k minus n plus 1, because I'm going to use 1 more than my derivative, times 1 plus x to the k minus n. So when I'm doing Maclaurin, so c is 0, so f of 0 is just 1, f prime of 0 is k, f double prime of 0 is k times k minus 1, f triple prime of 0 is k times k minus 1 times k minus 2, and so on. So my nth derivative, evaluated at c equals 0, is k times k minus 1 all the way, and I'm out of room, k minus n plus 1. So what does my series look like? Let me expand here. My series is going to be 1 plus kx plus k times k minus 1 divided by 2 factorial times x squared plus, okay, I'm tired of writing these, k times k minus 1 all the way up to k minus n plus 1 divided by n factorial all times x to the n. So this is what my series looks like. Let me do the n plus, let me do the ratio test. If I look at the ratio test, I really don't want to write all this down, but I will. Let's look at the limit as n approaches infinity of k times k minus 1 all the way out to k minus n plus 1. Oh, I need one more term, k minus n minus 1 plus 1, because I put in an n plus 1, divided by n plus 1 factorial times x to the n plus 1. And this is all going to be over, and yes, I have absolute value signs here, I'm just losing them, k times k minus 1 up to k minus n plus 1 times x to the n all over n factorial. Now, I'm going to do this a little early because this is just a pain. Okay, that term's going to go away. All of these terms are going to go away. All right, so this is the limit as n approaches infinity of the absolute value of x times k minus n divided by n plus 1 factorial. And this is going to be times n factorial, because I'm going to flip my denominator there. I didn't get rid of my whole denominator. So this is a limit as n approaches infinity of the absolute value of k minus n times x divided by n plus 1. All right, and this limit as x gets really, really big, let me extend my page here. That's going to be 1. So it's just the absolute value of x. So this is going to converge for all x less than 1. So you have a radius of convergence of 1. And the interval is from -1 to 1. Now you notice we didn't say anything about what k was here. So what do you do when you look for a power series expansion for something like this, the cubed root of 1 plus x? Well, I don't want to do all these derivatives, and neither do you. So what I can do is I can say 1 plus x to the k is equal to 1 plus kx plus k times k minus 1 x squared, divided by 2 factorial, plus k times k minus 1, k minus 2 x cubed, divided by 3 factorial, plus and so on and so on. All right, I need to identify what k is. For this, k is 1/3. So I can write that 1 plus x to the 1/3 is equal to 1 plus 1/3 x plus. All right, now this is going to get a little messy. 1/3 times 1/3 minus 1 divided by 2 factorial x squared plus 1/3 times 1/3 minus 1 times 1/3 minus 2 x cubed divided by 3 factorial, and so on. So let me rewrite this a little bit more simply. This will become 1 plus x over 3 minus, because that's going to be negative, 2x squared divided by 3 squared times 2 factorial plus, and I'm going to leave it this way, 2 times 5x cubed divided by 3 cubed, 3 factorial, and so on. Now, you can find a general form for this, but in general on these, you're only going to need to find the first 3 or 4 terms.